Hello everyone. Hello everyone. Hello. Today we are going to learn the various laws of motion. And you see in laws of motion what truly governs motion. For millennia, humanity has sought to understand the forces that shape our world. We have moved from simple observation to a profound understanding of the universe. This is the story of the journey. The ancient answer: a force is needed to keep things moving. You can see the Greek thinker Aristotle observed the world and concluded an external force is required to keep a body in motion. This feels right. A child knows they must keep pulling a toy car for it to keep moving. If they let go, it stops. But our intuition has a flaw. Consider a skater gliding on ice or a stone sliding on a smooth surface. Once moving, they continue with almost no effort. The simple observation puzzled thinkers for centuries and held the key to a new science. What force keeps them in uniform motion? The hidden culprit, that is friction. Aristotle's view was flawed because it didn't account for the ever present opposing forces of friction and air resistance. To keep an object in uniform motion, the applied force only needs to cancel the force of friction. The net external force on the object is zero. Here you see that net force is zero, that means constant velocity. To keep an object in uniform motion, the applied force only needs to cancel the force of friction. The net external force on the object is zero. Galileo's leap of imagination. Galileo imagined a world without friction. Reasoned that a ball on a double inclined plane would try to reach its original height. See here, you can see that he reasoned that a ball on a double inclined plane would try to reach its original height. This is the original height. And the second plane were made horizontal. The ball would never reach that height and would therefore roll on forever. You see, this is infinite motion. This is Galileo's leap of imagination. Here you see, the first one reasoned that a ball on a double inclined plane would try to reach its original height. The second plane were made horizontal. The ball would never reach that height and would therefore roll on forever. Right? Now you see, next thing, that is Newton's first law. And what do you call it as the law of inertia? Isaac Newton formulated Galileo's insight as his first law of motion. Every body continues in a state of rest or of uniform motion in a straight line unless compelled by some external force to act otherwise. In short, if the net external force is zero, acceleration is zero. Inertia is an object's resistance to a change in its state of motion. Inertia is an object's resistance to a change in its state of motion. Newton's second law, force causes acceleration. Here you can see when a next external force acts on a body, it accelerates. This law defines the relationship. The rate of change of momentum of a body is directly proportional to the applied force. Rate of change of momentum. What is that rate of change of momentum? That you have to understand. We know that momentum is equal to mass into velocity. What is the momentum? Mass into velocity. You find the change in momentum, that is mv minus mu. That is change in momentum. And if we divide it by time, the rate of change in momentum, and that is equal to force. The rate of change of momentum of a body is directly proportional to the applied force, or kf mv minus mu by t. And if we take m as common, then we get v minus u by t. Or you can write here in this way, that's m into a, that we are getting force is equal to mass into acceleration. And so remember that the direction of force and direction of acceleration will be same. So we are getting that is F equal to ma. And what you find that the direction of force and the direction of acceleration will be same. In this way, we can define this force. Here what it says, the law defines the relationship, the rate of change of momentum of a body is directly proportional to the applied force. If we do in this way, F is directly proportional to the rate of change of momentum mv minus mu by t. Or you can write it this way, F is directly proportional to, if we take m as common, that is v minus u by t. And you know that is F is directly proportional to m, and v minus u is nothing but acceleration. If we write F is equal to, that is the constant k into m into a. And here the force is defined in such a way that the value of k is equal to 1. And therefore we are getting F is equal to ma. Here what you have to remember, that the direction of force and direction of acceleration will be same in this case. Direction of force and direction of acceleration will be same here. In this way, we can find Newton's second law, the force causes acceleration. When a net force, external force acts on a body, that is F equal to ma, and the direction of force and acceleration will be same. Next, what we find here, Newton's third law, forces always occur in pairs. Therefore, here you see that this one, F, is stone on earth, F, earth on stone. To every action there is an equal and opposite reaction. This means force are mutual interactions between two bodies. Key clarification: action and reaction forces act on different bodies, so they never cancel each other out. So you can say three things in this action reaction or Newton's third law of motion. The first one, the first one is that actions reactions are equal. Action and reactions are equal. Actions and reactions are equal. Number two, action and reactions are opposite. Action and reactions are opposite to each other. The third point, what you say, that action and reaction act on different bodies. That action and reaction act on different bodies. Act on different bodies. So here you find that action and reactions act on different bodies, and Newton's third law, that is forces always occur in pairs. You can see here, force, earth and stone, force, stone on earth, it is always in occurs. Action and reactions are, from this law we get 3 points. Number one, action and reactions are equal. Action and reactions are opposite to each other, and action and reactions act on different bodies. These 3 points you remember for Newton's third law of motion. Now we will get to another thing, that is this one. Consequence. What is the consequence of this third law? Conservation of momentum. In any isolated system with no external forces, the mutual forces between particles cause changes in individual momentum. But since these forces are equal and opposite, the changes cancel out. Total momentum of an isolated system is conserved. Here this part, the total momentum of an isolated system is conserved. We said it is before. This is total momentum 0, and here you see total momentum P plate plus P gun equal to 0. Here you find that total momentum of an isolated system is always conserved. The total momentum of an isolated system is conserved. The consequence, that is conservation of momentum. In any isolated system with no external forces, the mutual forces between particles cause changes in individual momentum, but since these forces are equal and opposite, the changes cancel out. The next point, what we get here, you see here, is the laws in action. Understanding friction. First of all, we learn these laws. How we find the laws you see here. Friction is the component of contact. Friction is the component of the contact force parallel to the surface that opposes relative motion. We have 2 types of friction. One is static friction. And another one is kinetic friction. In static friction, a self-adjusting force that prevents motion up to a maximum limit. Therefore, Fs is less than or equal to mu s into n. This is the F is equal to mu s into n. And kinetic friction, a constant force that opposes motion once it has started, that is F equal to mu k into n. Uk. This is less than or equal to, but in case of kinetic friction, it is mu k into n. So this is the difference between them. So the laws in action, understanding friction. So we found it here that right? Now you find that this is the applied force and find that this is the frictional force. This is static friction region. It is 45 degree. The motion Fx maximum motion begins from here to here, you see here. And after that, the kinetic friction will be less than the static friction. You see here, the static friction is always greater than the kinetic friction. And this is Fs is less than or equal to mu s into n, but kinetic friction is mu Fk equal to mu k into capital N, where is the n is the normal reaction, where n is the normal reaction. Now we will find another things also, that is friction is a component of the contact force parallel with the surface that opposes relative motion. Static friction is self-adjusting force that prevents motion up to a maximum limit. Kinetic friction is a constant force that opposes motion once it has started. So you can see in this graph that this one, that is, this is the frictional force in y direction and applied force in x direction, and the static friction is goes at an angle of 45 degree, and mu s, the maximum motion begins. After that, the friction reduces, and then kinetic friction. This is the kinetic friction region. This is the static friction region, and in kinetic it is less. You see, the curve goes down. In this, you can explain about friction. Next important thing is application. The physics of a road trip. The only external force that can accelerate a car along a road is the static friction between the tires of the road. You see, this is the normal force. This is the frictional force, propulsion. This is the weight of the car. In the front, it is air resistance. Acceleration. In acceleration, you know the net force is greater than 0. Constant velocity. At constant velocity, net force is 0. The force from the engine balances air resistance and friction. Braking, net force is less than 0. This is the applications, the physics of a road trip. This is the application of a physics of a road trip. Now you can see the physics of a road trip. The only external force that can accelerate a car along the road is the static friction between the tires and the road. This is air resistance, this is weight, this is normal force, this is frictional force, propulsion. Here you find accelerating, net force is greater than 0. Constant velocity, net force equal to 0. The force from the engine balances air resistance and friction. Braking, net force is less than 0. Now come to the point. Next point is, you see this one, application. The physics of the turn. The physics of the turn. And find the physics of the turn. Application: the physics of the turn. An object in circular motion is constantly accelerating towards the center. You see here, this is centripetal force provided by friction. An object in circular motion is constantly accelerating towards the center. According to force equal to ma, there must be a net force towards the center. This is called the centripetal force. And the centripetal force is governed by formula mv square by r. It is not any force. It is a net force provided by other forces like tension, gravity or friction. So the centripetal force is mv square by r. This is the physics of the turn. An object in circular motion is constantly accelerating towards the center. According to F equal to ma, there must be a net force towards the center. This is called the centripetal force. Fc is equal to mv square by r, that is centripetal force equal to mv square by r. mv square by r is the acceleration. It is not any force. It is a net force provided by other forces like tension, gravity or friction. It is find what is given in the next. Engineering the turn. Engineering the turn. Banked roads. If you got a banked road, here you see this is the banked road. Here you see this is the weight of the car mg. This is the normal reaction perpendicular to the surface. This is a centripetal component of normal force. This is a centripetal force. This is a centripetal component of normal force. Okay, and this is the r radius. By banking a road at an angle, the car's own normal force can provide some or all of the necessary centripetal force. This reduces the reliance on friction and allows for higher speeds. At the optimum speed, V0 equal to root over Rg tan theta. No friction is needed at all. So this is the engineering the turn. You can see here this is the weight, this is the normal force, centripetal component of normal force. So there is no friction is needed at all to turn this car in banked roads. So this is the engineering. We take this, that V0 at the optimum speed, V0 equal to root over Rg tan theta, and it gives the component of normal force. Now we learn the next thing, that is from a falling stone to orbiting planets. Newton's three laws, built on Galileo's foundation, unified the physics of the heavens and the earth. The same principles that govern a kicked football also govern the motion of the moon around the earth and the planets around the sun. They are the foundation of classical mechanics. Newton's three laws, built on Galileo's foundation, unified the physics of the heavens and the earth. The same principles that govern a kicked football also govern the motion of the moon around the earth and the planets around the sun. They are the foundation of classical mechanics. You learn the next thing, that is this one, the three pillars of mechanics. The three pillars of mechanics is, the first one, the law of inertia, the law of acceleration, the law of action and reaction. The first case, you see an object's velocity is constant unless acted upon by net external force. The if summation f equal to 0, then acceleration equal to 0. The law of acceleration, the net force on object is equal to its mass times its acceleration. That is summation of f is equal to ma. Summation of f is equal to ma. And the third one, the law of action and reaction. To every action there is an equal and opposite reaction. The force A on B equal to minus force B on A. These are the three laws, three pillars of mechanics. the law of inertia, the law of acceleration, the law of action-reaction. An object's velocity is constant unless acted upon by net external force. That is, if summation of force is 0, then acceleration will be 0. The law of acceleration, the net force on an object is equal to its mass times its acceleration. Summation F equal to ma, the law of action-reaction. For every action, there is an equal and opposite reaction, that is, force A on B is equal to minus of force on B on A. These are the three pillars of mechanics. These are the. So we have learned all the various the Newton's laws of motion. Dear friends, if you like this video, please subscribe, like and share. Thank you everybody for watching this video.